Hello, my name is Andrei and I'm here to teach you about microservices for ML. In particular, today I'll be talking about TensorFlow, microservices running on Kubernetes, and these microservices will be communicating through RabbitMQ, and the endpoint would be exposed through FastAPI. So basically this is a topic of MLOps, right? And the main challenge with ML is the data transfer, data processing, data preparation, model training. About model prediction, we'll talk other times. So I'm not talking about model prediction. I'm just we'll talk in this video about data processing, preparation, and model training. So it's nice to split model processing and training into different containers, right? And then the problem with microservices comes with communication between those services, especially when the service is producing data file, for example, and you need to store it somewhere so that other service should be able to access it. You could store files on external file location, whatever. Probably it works, obviously, but also it's convenient to keep data in the same infrastructure and still to be able to run microservices on Kubernetes in the cluster. So the problem is how you would run a container for data processing and for training. Would you run these containers in separate pods, or would you run in one pod? So I was studying this topic quite in depth, and I came to the conclusion that the most logical and practical way for data preparation and for model training containers to run in the same pod, where model training would be model training container would be the main one, and data processing would be would run as a sidecar container. And the main reason for this, because when containers run in the same pod, they share the same file storage, and both data processing container would need to store a file, for example, statistical information about a data set, so that later another container would be able to use this information to normalize the data in the same way as it was normalized for training, when we'll do predict functionality. And at the same time, model container also needs to save the data, save the file, model file, the trained file, so it also goes to disk. So both containers, they save to data, to disk, and in Kubernetes you could use like empty dir storage, which works until the pod is on. If pod is restarted or moved to another node, then that storage should be lost. Another thing you could do, you could use persistent volume with persistent volume claim, and you could specify volume class. And if you're testing locally, you could use a host path, so the data files will be stored on the host. And if you move to cloud, you could replace volume class with some other class that's supported by a specific cloud vendor, and you could just use another kind of storage. And with persistent volume attached to the pod, the same volume can be accessed from main container and from sidecar container. They see the same data, and you can mount this volume into different folders for main container and for sidecar container. I'll show you how you can do this. Yeah, and still communication between data processing container and model training container can be done with RabbitMQ for event-based communication, and all this microservices backend logic can be exposed to the outside through FastAPI application. So this is the introduction, and now let's go and see how it works as usual. And here you can see the diagram of our product Skipper. Whatever I'm showing and explaining in this video, all the source code is available online on a GitHub repo. So the link will be below the video. So go there and explore. Everything is there, and give us a star if you like it. So thanks. And today we'll talk about data and training microservices. I'll show how we package those containers in the same pod and how we set up persistent volume and volume claim for that pod so that data storage is accessible from both containers. Okay, so now let's go and let's see what pods are actually running on this environment, because the environment is already up and running, and I could just go and copy paste this command to list pods. Okay, copy it and go over here. Okay, I see that we have API pod is running. This API pod basically runs FastAPI application, then API salary pod, which is responsible for background task execution. Then there's a logger workflow pod, which are helper pods in Skipper infrastructure, and then there's a training service pod, and this pod runs two containers, training and data service. Okay, so now let's open logs, and first of all let's open logs for the API service. Let's go to the API, and this is the command which can help us to open the logs on API container. Let's open it here in the third window. API container is set with liveliness probe, and if something happens bad to the container, pod just restarts the container and it becomes up and running again. Okay, then okay, so then we all can open log for the salary pod as well, so that we could see how salary executes when a request would come. So in that separate window. Okay, and then let's open also log for training pod, and this pod runs two containers, training and data. Let's open log for training container. So the command is in the services, training service, and yeah, we got, yeah, but maybe before we would open the log, let's enter into the training container and see if there are any files like model or statistical files are already generated or not. And we could also check if persistent volume claim was already created. Yeah, and we can see that in our namespace Katana Skipper, there is a training service claim is created, and if we check persistent volume, we can see that this claim is running on top of training service volume, and this volume is stuffed with host path class. By default, when you want to share, usually if you go to the Kubernetes documentation, you would see that when you want to share files between containers running in the same pod, you would use empty dir storage, and the storage would be destroyed when pod is restarted. But on purpose, I'm using host path so that when model is trained and if pod is restarted, I don't want to lose the model. I don't want to retrain it again. If pod will be moved to another node, then obviously host path storage would not be available there. That's fine. In that case, model will be retrained. And you could actually force pod to run on the same node, but unless something really bad happens to the node, then Kubernetes move the pod to another node, and then training, you would need to retrain the data. But if you run this pod in cloud environment, you could set up, you can change the host path class to some cloud storage, and then even the pod would move across nodes, the volume still would exist because it would not be attached to certain nodes. But host path is fine for local testing. Okay, so volume is available, and okay, we can let's enter into the training container running on training pod, and we need to replace container name for to be able to access into the container. Sorry, pod name. So we replace the pod name and we enter into training service container. Inside we can list the content. We can see models. So let's go into the models and list. So it's empty. Right, it's fine, and now we'll execute training request and we'll see that files should be generated. Okay, now let's open the logs for the training container inside training service pod. Okay, so we got the logs, and I was executing training before, so this is the log from the last time. That's fine. We'll execute new training until you see logs updated. Okay, so we got logs for salary, for API, and one more thing. Let's open RabbitMQ UI to demonstrate to you that message is actually is sent to the queue and it's visible through the UI dashboard. Okay, let's let's go to main folder, and over here we can see that for the RabbitMQ I have instructions listed. If running on local Kubernetes, we need to expose the port for the RabbitMQ UI dashboard, and let's do it here. 15672 is exposed, and then we can copy URL and navigate to the application, and we can log in with username skipper welcome1, and we can see there was one message was sent before, and let's see now when execute request we should see that statistics would be changed. Okay, so we saw the pods, we enabled all the logs, and we saw that there are no model training file. Model file is not, it does not exist in the directory. So let's go to FastAPI endpoints. Let's test it. It runs fine, and by the way, we can go to the logs, and we can see that when we execute the new get is actually message is reported. Let's do something like that. Let's put it down over here and execute. We see request goes to the Skipper API pod, to the API container, and log is printed. So API is up and running, and now we can do a post to asynchronous message which will be handled by API pod, and then another pod, it will be submitted to the salary pod, and salary pod would send the event to RabbitMQ to initiate the training. The message will be delivered to the training pod, to the main training container. Training container would send message to the data processing container. Data processing container will prepare data, send it back to the training container. TensorFlow would execute, would produce the model. Model will be saved on disk, and response will be returned. So let's go over here. We don't need that part, and payload should be 0.2, and for the description, let's say this will be some sample call. And for the log, let's open training container and we execute. So we should, okay, the training was done, log was printed, and over here for the salary log we see that task was completed and there was post request was successfully received by the API. And to make sure to verify that training is completed, we could copy the asynchronous task ID from the response of the training and go to another endpoint where we could check the status of the task. We execute and we see the task is completed. That's fine. And if you go again into the training container, we see that it reports statistics of the model training and also reports data statistics about the data. Okay, now let's exit from the log and let's open, let's enter the container for training, the same like we did last time, and let's go to the models and list the files. Now we can see that model folder was created with TensorFlow model, and also this is train stats CSV is created. This is a statistics file generated by data processing container, and this data could be used to normalize data in predict container when predict function will be executed. Okay, so we exit from here, and this is basically all runtime. And now let's switch to PyCharm and see how basically training pod with main training container and sidecar data container was defined. So first of all, this persistent volume is created, and the main storage class name is defined. It can be any name, it's just an identifier. Then we are assigning capacity to this volume, and we say that this volume can be, we can write to that volume by one pod. And the most important thing is a host path. And on your Kubernetes environment, you could run kubectl get storage class, and as output you would see which storage technology is supported. So if I do it on my environment, because I'm using local Docker Kubernetes, it's a host path. If you run it on cloud, it would be some another stuff printed, and then you would define it as a host path over here. If it's something else, then you would follow documentation of the cloud vendor and use another storage technology, and just mount to the directory on the host path. This can be any directory. Mount data is kind of standard if you follow documentation. So persistent volume defines place for the storage, and then persistence volume claim is another level of abstraction where you refer to the class name host path, but you don't specify underlying storage technology like host path or something else like we did in volume in persistent volume definition. And yeah, here you can assign the storage that you would claim from the entire volume. And then finally we have a pod definition, and we define two containers for the pod. So the first one is a training service, and we mount for the training service, we mount to that path. And for the data service, for the data container, data service, I have another container, and we mount also in the same data space, in the same space which is called, we call data. It could be any other name. We refer to its own path. But we have data service models, and we have over here training service models. So for the containers, folder naming is different, but essentially both folders would point exactly to the same place, because both containers, they're using the same persistence volume. So physically, any files that will be written by training service, they will be visible in data service and otherwise around as well. And this data is over here defined under volumes, and it points to the persistence volume claim that was defined in another YAML definition file. Okay, so hopefully this gives you a feeling of how you would run TensorFlow or another ML framework along with data processing container in the same pod, and also it gives you a feeling how it runs in microservices environment when you have separate pod for API with FastAPI framework. Then you would have another pod with Celery, which allows asynchronous request execution, which doesn't block REST API. Then you have pod with main and sidecar containers. What I'll be showing next probably is how you fit model usage prediction functionality into this architecture. And this would be another pod. So I don't want to run prediction container in the same pod with training, because prediction functionality should be scaled separately from the training functionality, because it runs on its own and it should be scaled independently. So this means you should run in a separate pod, but it's a bit tricky because we need to get the model file from the training pod and pass it to the prediction pod. So let's see how it can be solved in my next video probably. So thanks for watching, and see you next time. Bye.